Good day, everyone. Welcome to Chemical Engineering Laboratory 3. This course is an important bridge between your academic theory and the real-world application of chemical engineering principles. By the time you finish, you should not only know how to design and conduct experiments but also how to think critically about the data you collect, troubleshoot problems, and connect laboratory-scale results to industrial-scale processes. This is an advanced laboratory course, so we'll be building on your prior experience from earlier lab courses, especially in areas like fluid mechanics, heat and mass transfer, thermodynamics, and chemical reaction engineering. Today, we'll walk through the essential knowledge, techniques, and expectations that will guide you throughout this laboratory course. We'll cover safety, experimental planning, working with advanced equipment, collecting and analyzing data, understanding sources of error, and linking results to chemical process design. We'll also talk about how labs like this prepare you for the realities of chemical engineering in industry. 1. The role of the laboratory in chemical engineering. Before we start, let's set the context. Why do we even have advanced laboratory courses like this one? Chemical engineering is not only about equations on paper, it's about understanding processes in practice. The laboratory allows us to apply theoretical concepts in a controlled setting, gain hands-on experience with industry-standard equipment, develop problem-solving skills for unexpected situations, practice working with data, uncertainty, and variability, learn professional habits like proper record-keeping, teamwork, and safety compliance. By now, you've probably noticed that real systems rarely behave exactly like the perfect models in textbooks. In the lab, you'll see how non-idealities, like heat losses, pump inefficiencies, or measurement delays, affect real data. 2. Laboratory safety and responsibility. I cannot overemphasize this, safety comes first, always. Even though our experiments are at laboratory scale, the chemicals, pressures, and temperatures we deal with can be dangerous if not handled properly. You are responsible for protecting yourself, your colleagues, and the facility. Key safety expectations. Always wear proper PPE, lab coat, safety goggles, closed-toe shoes, and chemical-resistant gloves where appropriate. Know the location of safety showers, eye-wash stations, fire extinguishers, and emergency exits. Never work alone in the lab, always have at least one other trained person present. Label all containers clearly with the chemical name, concentration, and hazards. Avoid eating or drinking in the lab. Before starting any experiment, you should conduct a hazard analysis. Ask yourself, what chemicals am I using? Are they flammable, corrosive, toxic, or reactive? What equipment hazards exist, such as high pressure, high temperature, or moving parts? How will I minimize these risks? 3. Planning an experiment. Jumping straight into an experiment without planning is one of the most common mistakes students make. Advanced labs require methodical preparation. Before you arrive at the lab, you should understand the theory behind the experiment, know the governing equations, key variables, and expected trends. Review the procedure, not just skim it, but really think through each step and what it achieves. Identify control variables, kept constant, and independent variables, you change during the experiment. Prepare data sheets for recording measurements. This keeps things organized and ensures nothing gets missed. Check calibration of instruments to ensure accurate readings. For example, if you're running a heat exchanger experiment, you should already know the inlet and outlet temperatures you measure, the flow rates you set, and how you'll use those numbers to calculate heat transfer coefficients. 4. Understanding the equipment. In Chemical Engineering Laboratory 3, you'll likely encounter more advanced and larger-scale apparatus than in earlier labs. These might include distillation columns, packed or tray type, fluidized bed reactors, continuous stirred tank reactors, CSTRs, and plug flow reactors, PFRs. Heat exchangers of different configurations. Filtration and separation units. Process control setups with programmable logic controllers, PLCs. Your goal is not just to run the equipment but to understand how it works. This means knowing the flow path of materials, how measurements are taken, and how the system responds to changes. For instance, with a distillation column, you should know where the feed enters and at what conditions, How the reboiler and condenser operate. How changing the reflux ratio affects separation. What instrumentation is used to monitor temperatures and compositions. 5. Data collection principles. Data collection in advanced labs needs to be systematic, accurate, and repeatable. A few golden rules. Record data immediately, never rely on memory. Note all conditions during the run, including room temperature, barometric pressure, and any unexpected events. Take multiple readings for the same condition to account for variability. Use proper units consistently. Sometimes, data may not make sense on the first look. Don't panic. First, check if the readings are physically reasonable, then think about possible sources of error. It's also common to run preliminary trials just to see if the system is stable before collecting the final dataset. 6. Data analysis. Once you've gathered your measurements, the real thinking begins. Analysis is where you turn raw numbers into engineering insight. For example, in a reactor experiment, you might calculate conversion, selectivity, and reaction rate constants. In a heat transfer experiment, you might determine the overall heat transfer coefficient. In fluid mechanics, you might plot pressure drop versus flow rate to determine friction factors. Always compare your results to theory. Do they match? If not, why? Are the deviations due to measurement errors, non-ideal equipment behavior, or incorrect assumptions? Statistical tools like standard deviation, confidence intervals, and regression analysis are very useful here. They allow you to judge whether your results are within reasonable bounds. 7. Sources of error and uncertainty. No experiment is perfect. Understanding the limitations of your work is a mark of a good engineer. Common sources of error include instrument error, caused by calibration issues or equipment limitations. Procedural error, mistakes in following the method. Environmental effects, temperature fluctuations, vibrations, etc. Human error, incorrect readings or data transcription mistakes. In your lab reports, always discuss uncertainties and how they might have affected your conclusions. For example, if a thermometer has a plus or minus 0.5 degrees Celsius accuracy, explain how that impacts calculated heat transfer rates. 8. Process control and automation in the lab. In modern chemical plants, process control is critical for safety and efficiency. In this course, you may encounter experiments with control loops, such as temperature or flow control, using digital controllers or PLCs. Understanding control involves knowing the controlled variable, e.g., temperature. Knowing the manipulated variable, e.g., heater power. Observing how the system responds to disturbances. For example, a stirred tank reactor with temperature control will use a feedback loop to adjust heating when the temperature drifts from the set point. Learning to tune these controls, adjusting parameters to minimize overshoot or oscillations, gives you practical skills directly transferable to industry. 9. Linking lab work to industrial practice. One of the goals of Chemical Engineering Laboratory 3 is to help you see the connection between bench-scale experiments and full-scale industrial processes. Let's take an example. In the lab, you might run a distillation experiment with a small column, separating ethanol from water. You determine the effect of reflux ratio on separation efficiency. In industry, the same principles apply when designing massive distillation towers for petroleum refining or chemical production. Your understanding of column operation, pressure drop, and energy requirements translates directly. This link is important because scaling up is not a simple matter of multiplying numbers. Different effects like heat losses, mixing inefficiencies, and safety risks become much more significant at industrial scales. 10. Report writing and communication. In this course, your work doesn't end when the experiment is over. Communication is a vital engineering skill. A good lab report should describe the purpose of the experiment and the theory behind it. Explain the procedure clearly enough for someone else to repeat it. Present data in well-organized tables and graphs. Analyze the results critically, don't just restate numbers. Discuss limitations and suggest improvements. Think of your report as a professional document, something you might present to a supervisor in an industrial setting. 11. Teamwork and professional conduct. Most experiments in this course are team-based. This is intentional. Chemical engineering in industry is almost always collaborative. Good teamwork involves dividing responsibilities clearly, communicating openly about results and issues, supporting each other in troubleshooting problems, respecting deadlines and each team member's contributions. Professionalism also means showing up prepared, treating equipment with care, and respecting lab schedules. 12. Troubleshooting skills. In advanced labs, things sometimes go wrong, pumps fail, instruments drift, readings fluctuate. Part of your learning is developing a systematic approach to solving these problems. The troubleshooting process often involves observing the symptoms carefully, checking the simplest possible causes first, using knowledge of the system to narrow down possibilities, testing one change at a time so you can see its effect. For example, if a flow meter reading is unexpectedly low, check if a valve is partially closed before assuming the instrument is faulty. 13. Ethical considerations in laboratory work. As future engineers, you have ethical responsibilities. Never falsify or manipulate data to fit expected results. Report safety incidents honestly, no matter how small. Acknowledge contributions from all team members. Dispose of chemical waste according to environmental guidelines. Integrity in the lab builds trust in your future workplace. 14. Final thoughts on the course. By the end of Chemical Engineering Laboratory 3, you should be comfortable planning and executing complex experiments, operating advanced chemical engineering equipment safely, analyzing and interpreting experimental data, recognizing sources of error and uncertainty, linking lab-scale results to real-world processes. Think of this course as your transition zone. You're moving from being a student who studies engineering to being an engineer who practices it.